All right, hi folks. In this video, we're just going to go over some very common reaction types that are typically included in an electrophilic aromatic substitution chapter, as well as some of the corresponding functional group manipulations that are typically included in the same chapter or the chapter thereafter. And so again, if you want access to these PDF files so that you can fill them out in advance all on your own, please go ahead and follow us as a patron subscriber. And that way you can download both the blank PDF sheet ahead of watching the videos, but then also the answers after the fact. All right, and so this is 5 reactions that are pretty common for those of you studying electrophilic aromatic substitution and the reactions of the corresponding benzylic functional groups. And so what I'm going to do here is pause the video and give you an opportunity to try to solve these and fill these in all on your own, and then see how you did after the fact. So go ahead, pause, take a few minutes, work them through on your own. Okay, hopefully you're coming back to us now. And what I'll do is just go ahead and start up here at A. And under these conditions, what we should try to do is identify what the key reaction is. And so here we have a benzoic acid kind of as our frame of reference, and we're going to end up nitrating that benzoic acid. And specifically, the nitration is going to be meta to the benzoic acid. Now that's really convenient for us because the benzoic acid is going to be a meta directing group. It's fairly strongly withdrawing or deactivating. But thankfully, it's not so deactivating that we can't nitrate the system. And this looks then like a no-trick electrophilic aromatic nitration reaction. And so we can go ahead and just put in our favorite mixed acids. So HNO3, and then we need H2SO4 to protonate the nitric acid. And so those are kind of the classic mixed acid nitration conditions. And that should take care of that one. All right, for this next one, we're asked here to think backwards and actually put in what's the starting material. And so to identify that, we need to know what these reaction conditions tend to do. And this zinc-mercury amalgam is actually the Clemmensen conditions, especially under strongly acidic conditions with HCl. Okay, and so that's the Clemmensen reaction. And the Clemmensen reaction or reduction is one that removes a carbonyl oxygen from a benzylic position. And so thankfully we have a CH2 here in the product to use as a guess where that carbonyl would have gone. And so if we can identify the Clemmensen reduction, then we should be able to go ahead and fill this in as the more oxidized starting material. So there we go. So that should be our ketone starting material. And in the forward direction then, if we expose that to the Clemmensen reduction conditions, we'll remove that benzylic oxygen and replace it with 2 hydrogens right there. Okay, moving down to C. This one is, let me see here, bromine. So that's a very common electrophile for an electrophilic aromatic substitution. We're given a modestly strong base, so sodium bicarbonate is not a strong base, but it is a weak buffering base. And then if we look at our starting material here, we'll notice that we have 2 activating groups, both the NH2 and the CH3. And so whenever you have to do an electrophilic aromatic substitution on a ring that has more than one group, I always encourage people to identify what's the strongest activator. And so real quick, if I have to label these, I would say that this is a weak activator, but this NH2 is a strong activator. And so it turns out that that's going to be super important because remember, electrophilic aromatic substitution is going to be dictated by the strongest activating or directing group. And then if we know that, we should also recognize that the NH2 is an orthopara director. And so that means that it's going to direct to one of the 2 green spots here. And now we have to consider if we need a catalyst. So remember, if you're going to brominate benzene, often we have FeBr3. But as you increase the reactivity of that aromatic ring, it becomes less and less necessary to have that Lewis acid activator. And phenolic, so OH groups, or in this case, anilines with that NH2, they're going to be so electron donating, so activating, that you don't even need that iron bromide intermediate. It actually complicates the reaction. And so bromine all by itself is going to be enough to do that electrophilic aromatic substitution. Now, one downside of using a ring that is so activated is it sometimes becomes susceptible to overbromination. And that's probably what would happen in this particular ring. Is that after you undergo one bromination, the ring is still going to be very, very activated by the NH2, and it'll probably undergo a second activation. And this weak base is here to help out because after that first reaction, you generate HBr. And the aniline is going to be basic. And so that basic aniline will actually form the HBr salt, and that would significantly deactivate the ring system. And when it deactivates the ring system, it also actually becomes a meta-directed group. So because of that full positive charge, all of a sudden it goes from being strongly donating to very powerfully withdrawing. And that's going to really hamper the reactivity. And so we need a weak base to help soak up all the HBr. Now, some of you might be wondering, if that's true, can you pause the reaction by having it generate HBr and then halt the reaction at that stage? In principle, that sounds like a good idea. The difference is that both the starting material and the product are anilines of about the same basicity. And if anything, the starting material is probably a little bit more basic because the bromine is a weakly withdrawing group. And so that means that the starting material is slightly more electron rich and might be slightly more basic. And so if you ran this reaction in the absence of excess bromine with only one equivalent of bromine, and if you ran it without the base, what you'd probably get is a mixture of the dibrominated material, the starting material, and both isomers of the monobrominated material. And so that really complex mixture then isn't really one that we'd want to deal with. And so the easiest thing to do here is to actually overbrominate the whole thing in the presence of base and get the dibrominated product. Okay, two more here at the end. And so this one looks like some familiar reaction conditions. And so here what we have is aluminum trichloride and an alkyl halide. And so that should right away trigger the Friedelcrafts reaction. And that would be good because over here we have a modestly electron-rich aromatic ring. And I'll point out a couple of things here, one of which is that this problem very clearly says we're going to use excess of the dimethylbenzene. And that's going to be important because remember, the products of Friedelcraft alkylation reactions are actually more reactive than their starting materials. And so if you have limiting chloride, you can prevent that over-alkylation. If you try to use a limiting amount of the arine, sometimes you can end up with di or tri over-alkylated material with the Friedelcrafts alkylation. Remember, that's one of the advantages of using the Friedelcrafts acylation is it keeps that from happening. The other thing I'll point out about the starting material is because it has not one, but two methyl groups on it, it's a modestly electron-rich ring. And remember, that's very important because as the Friedelcrafts reaction interacts with weaker and less active aromatic rings, at some point it just shuts down and it stops working. And so typically you need to be in the electron-rich regime for a good Friedelcrafts alkylation reaction to occur. Okay, so here the aluminum trichloride and the propyl chloride want to come together to make a carbocation. And that's usually what we think about actually doing the Friedelcrafts alkylation reaction. The downside here, though, and one very common pitfall, is that this primary carbocation is going to be prone to a 1,2H shift. And so it's going to make the secondary carbocation as a function of that. And so our product should undergo the Friedelcrafts reaction, but it should do so at the secondary carbon. The other nice thing about this starting material is because it's symmetric this way and symmetric this way, all 4 of those hydrogens are equivalent, and so we don't have to worry about if it's going ortho or para or not. It's just going to substitute at one position. But the most common pitfall in a question like this is students forgetting to rearrange that primary carbocation to the secondary carbocation as part of the Friedelcrafts reaction. Okay, last one here. And in this particular case, it's another one of these pesky fill in the starting materials. And sometimes those are often harder than the fill in the products because we have to think backwards. Okay, and so what I always try to do here is find a point of reference. And so the good news is we have a ketone that lines up, and we have a functional group at the meta position where we're going to make that new carbon-carbon bond. And so that's good. That means whatever has to go in the box has to contain that stuff over there. And the big clue here now is going to be palladium. And there aren't too many reactions where we invoke palladium other than reductions. And so there's not H2 gas here. And so this isn't our common reduction of an alkene or anything like that. But what it should tell us is that it's going to be some kind of cross-coupling reaction. And so in the aromatic substitution chapter, that's the most common occurrence of these. And that's convenient because the bond we have to make here is an sp2 sp2 carbon-carbon bond. And those are exactly the ones that we like to put together with cross-coupling reaction. And the most common cross-coupling reaction here is going to be the Suzuki cross-coupling. And so we can go ahead and put in our boronic acid over on this side. And for those of you that are wondering if there's more than one correct answer to this, there certainly is. We could really put in any M group here, where M stands for an organometallic. The Suzuki is the most common and most popular of these cross couplings, but M here in bracket could equal, let's say, magnesium chloride or magnesium bromide. It could equal SN-butyl 3, so that would be the Stille reaction. And we could even put in zinc for a Negishi, so maybe it could be zinc chloride or zinc bromide. And so there's a wide variety of these organometallic starting materials that we could use with palladium to do this cross-coupling. If it were my class, I would grade all of them as being correct. The most common and popular of which, though, is going to be the boronic acid, which will be part of the Suzuki reaction. All right, so with that, thank you for paying attention. Again, if you've been enjoying these videos, please subscribe to the YouTube channel. That'll get you updates when we post more content. Also, please go ahead and follow us as a patron. That'll let you download the PDFs both before and after I've filled them out. And so that way you can work through them at home a little bit more efficiently when I ask you to click the pause button. All right, thank you, everybody. Please enjoy the next video.